In this first question, we are looking at charging time here for an iPhone versus a Samsung. Our iPhone here took 126 minutes to charge, and our Samsung took 108. Which phone charged faster relative to its specs, so relative to this charging distribution? So here we have the means and the standard deviation of the two distributions for iPhone charging and Samsung charging. And since we're comparing two different distributions, we're going to use z-scores here to compare. So if I go to our formula sheet here, we see z-scores right here. Z is x minus mu over sigma. Just go ahead and grab that. And we'll assume a normal distribution here. So the mean, that is going to be this column here. That's going to be our mu. That's our population mean. And standard deviation, that will be sigma. And then these individual values, the 108 and the 126, those are going to be x values. So now we can just plug into our formula for z-score here. So let's see. Let's do this for the iPhone. And for the Samsung. And we'll compute a couple of z-scores here. So for the iPhone, it took 126 minutes to charge. That's our x value. Minus our mean for iPhones was 120. And then divide by our standard deviation was 10. Do the same thing down here for the Samsung. So the x value there is the 108. Our mean there, 100. And then dividing by standard deviation, which was 20. So let's go ahead and put these in the calculator. So for the iPhone, we've got 126 minus 120, that's 6. 6 divided by 10, that should be 0.6. Yes. So this is a z-score of 0.6. And then 108 minus 100 is 8 divided by 20 is 0.4. So both of these are positive, and the iPhone, the charging is 0.6 standard deviations above the mean. For the Samsung, it's 0.4. So faster is going to be a lower charging time, so that's going to correspond to a lower z-score. So it's going to be the Samsung here. And just to give a picture here of what's going on, the iPhone distribution looks like this. So we've got 120 in the middle, and then 1, 2, 3 standard deviations to the right, 1, 2, 3 to the left. So that'll be, each standard deviation is 10, so 130, 40, 50, so that's 150. Let's see, 110, 190. So this distribution looks something like this. And then the individual charging time was the 126, which would be somewhere in here. And that corresponds to the z-score of 0.6. So this is 0.6 standard deviations above the mean. And then for the Samsung, in the middle is going to be our 100. 1, 2, 3 standard deviations to the right. Each standard deviation is 20. So 120, 140, 160. And then this will be 80, 60, 40. So that distribution looks like this. It's going to be more spread out than the distribution for the iPhone. And then our charging time's 108. So that's going to be about right here because this is 120. And that's 0.4 standard deviations above the mean. So it's a lower number of standard deviations above the mean. All right, let's see. Next up here, SAT scores of students are normally distributed, so follow a normal distribution, with a mean of 1,050 and a standard deviation of 50. The area between 900 and 1100 is 0.84. What is the interpretation of this area? So when you interpret a normal distribution, it's either the probability that a randomly selected individual data value is between the cutoffs that they give you, or the proportion of the total data. So we could say that a randomly selected SAT, that should be a C, has 0.8400, so has a probability of 84% of being between 900 and 1100. Or equivalently, the proportion of the data so the proportion of SAT scores between 900 and 1100 is 0.84 or 84%. So 84% of the SAT scores are between 900 and 1100. So that's just interpretation, because they're asking what's the interpretation. They're not asking you to compute. So we actually didn't use the mean 1150 and the standard deviation 50. It was just the 900 and 1100, the upper and lower cutoffs they gave us. Hip bone density is 0.81 grams per centimeter for a 65-year-old female, and that has a z-score of minus 0.65. Interpret this statement. So remember, z-score here is number of standard deviations above or below the mean. So this is number of standard deviations from the mean. So this is saying that 0.81 grams per centimeter squared is negative 0.65, so that would be 0.65 standard deviations, and it's below the mean because it's a negative z-score. Remember, positive is above and negative below, and it's always relation to the mean. So negative below and positive above. And it's always number of standard deviations. So it's a ruler, and your markings on the ruler are standard deviations. Use your calculator to compute the following. State your answers to 4 decimal places. So find the area under the standard normal curve, so that means z-scores. To the right of z is negative 0.86. So let's sketch a picture here. So for a standard normal distribution, we've got 0 in the middle. We've got 1, 2, 3 to the right, and 1, 2, 3 to the left. So negative 0.86 would be about right here. And we want the area to the right of that. So we want this area here. So we're going to use normal CDF to do this. So that area, which is actually the probability that your z-score is greater than negative 0.86, is going to be normal CDF And then remember you do lower cutoff, upper cutoff, mean, and standard deviation. So I'm thinking we had that on the formula sheet here. So area under the curve between normal CDF gives the area, inverse norm gives z-scores. Okay, yeah, so I mentioned normal CDF gives it, but the syntax is lower bound, upper bound, mean, standard deviation. So our lower bound here is at negative 0.86, so that's the left-hand cutoff. So this will be negative 0.86. The right-hand cutoff goes out to infinity. We'll use a big positive number, 10,000. Mean is 0, and standard deviation is 1 because we're talking about z-scores. Let's go ahead and put that in the calculator. So we want to go to the distribution menu, second variables, normal CDF number 2, lower bound negative 0.86, upper bound 10,000, and then mean standard deviation 0 and 1 because it's z-scores. Paste it, 0.8051. So 80.51% of the area is to the right of negative 0.86. Part B, probability z less than 1.08. So let's sketch our diagram here. So you got 0 in the middle, 1, 2, 3, 1, 2, 3. So 1.08 would be about right there. We want a less than, so to the left. So we want that area there. So probability z less than 1.08. Lower cutoff minus infinity. So we'll do normal CDF again. Lower cutoff minus infinity, we'll use negative 10,000. Upper cutoff right here, that's our 1.08. And then mean standard deviation, the same, 0, 1. So let's enter that in the calculator. Second variables, number 2. So negative 10,000, 1.08, and 0, 1. 8599. And then part C, probability z is between. So we sketch that distribution here. Z equals 0 in the middle. 1, 2, 3, 1, 2, 3. So negative 1.10 would be about right here. 1.86, 1, 2, so about right here. So we want that area right there. Oops, 1.10, less than z, less than 1.86. So that's going to be normal CDF. Lower cutoff, negative 1.1. Upper cutoff, 1.86. And 0, 1. Compute that. Second variables, number 2, negative 1.1, 1.86, paste it, 83289, so 8329. Next up, we are looking at some fasting glucose levels, which are normally distributed. So that means you can use normal CDF. with a mean of 100, so that's going to be our mu, and a standard deviation of 20, that's going to be sigma. A person selected at random, find the following. So if they're selected at random, these will be probabilities. So probability blood glucose level is above 130. So part A here, that's asking probability that X, an individual blood glucose level, is greater than 130. So the difference here between this problem and the last problem is, last one we were dealing with z-scores. Mean was 0, standard deviation was 1. Here our mean's 100, standard deviation 20. So if we sketch a picture on this, you're going to have your mean in the middle, 1, 2, 3 standard deviations right, 1, 2, 3 to the left. The mean 100 in the middle, and this will be 120, 140, 160. And this will be 80, 60, 40. So we want to know greater than 130. So 130 would be right here. Greater than is going to be to the right. So this will be normal CDF. Our lower cutoff is going to be the 130. Our upper cutoff, this goes out to infinity, we'll use 10,000. Mean is 100, and standard deviation 20. So let's go ahead and compute that in the calculator. So clear these guys out. So second variables, number 2 again. Our lower bound is the 130. Our upper is the 10,000. Our mean now is 100 and standard deviation 20. Paste it, enter 0.0668. So there's about a 6.7% chance that a randomly selected person would have blood glucose above 130. Part B. Probability blood glucose level is below 85. So that's asking what's the probability that X is less than 85. So then that picture, we still got our 100 in the middle. And 20, 40, 60, and 80, 60, 40. So 85 would be about right here. We want probability of less than 85, which is represented by the area to the left. So this will be normal CDF. Our lower cutoff, this goes down to minus infinity. We'll use negative 10,000. Our upper cutoff, 85, is the right side of the shaded area. Mean and standard deviations stay the same. So let's enter that in. So second variables, number 2, our lower negative 10,000, and our upper is the 85. And then the last mean standard deviation are all set from the last part of the problem. 2266. So 22.66% chance that someone's less than 85. Part C, between 95 and 125. So this will be 95 is less than X is less than 125. So that picture is going to look like this. Got 100 in the middle. Uh, 95 would be about right here. 125 would be about up here. And we want between, so we want that area right there. So our lower cutoff 95, upper 125. So normal CDF. And then we'll have 95, comma 125, and then 100 mean, 20 standard deviation. Let's compute that. So let's see, 95 and then 125. Everything else is the same. 49305, 4931. So 49.31% chance. And then part D. So D, the 95th percentile of blood glucose levels. So remember, the percentile is the number with that percentage below. And you'll use inverse norm for percentiles. So what we've got here is got our bell-shaped curve, 100's in the middle, 20, 40, 60, 20, 40, 60 below. So 100% of the data is everything underneath the whole curve. So 95% of the data would look something like this. It's going to take up almost everything except a little bit in the tail here. So we want to know, what is that value right there? And that's going to be inverse norm. So use inverse norm to get x values or z-scores. So this will be inverse norm. And then your syntax there, you put in the area to the left, which is 0.95. So 95% below. And then mean standard deviation. So 100 was our mean, standard deviation 20. So let's compute that. So second variables, inverse norm number 3. Area is left area, 0.95. Unless you, yeah, and ours is left. It's area to the left, 0.95. You could do 0.05 and mark right area, because the top 5% is the 95th percentile. So it's another way to state the problem. We'll come down here and paste. So 1.6448, 1.645 is, oh wait, I'm sorry. We did 0 and 1. That's a z-score of 1.645. Go back in there. Second variables, number 3. We need our mean of 100 and our standard deviation 20. There we go, 132.9. So 132.9 here is the 95th percentile, or it corresponds to the top 5%, because this area is 0.05, because 95 and 5 have to add up to 100. So they can ask this as a percentile question. They're giving you left area, or as a top so many percent, top 10%, top 5%, then they're giving you right area. So if they said top 5%, you either have to use right in the calculator, or you do 1 minus 0.05 is 0.95, and then you can use left area in the calculator. So those are very closely related. Number 6, we have a research study here that examined the amount of weight the participants lost in first 12 weeks on a new weight loss medication. A 99% confidence interval of the mean weight lost from 150 had a lower bound of 58 and an upper bound of 12.3. So what does it mean to say we are 99% confident the mean weight loss is between 5.8 and 12.3? So that's our lower bound, upper bound. So we're asking, what does this 99% confident mean? So remember, that's a probability statement about the proportion of intervals. So what this means is if we select repeated, let's see, this was size 150. So if we select repeated samples, of size 150, then 99% 99% of the confidence intervals obtained from those. So you do a whole bunch of samples of size 150, do a whole bunch of confidence intervals. 99% of those confidence intervals obtained will include the population mean, so mu. So that's population mean. So it's a probability statement about the proportion of confidence intervals that are going to contain that mean. And let's see here. So no computing there. So because it asks, what does it mean? What's the interpretation? And then number 7. Here we're actually going to do some computing. So we've got a random sample of 550 registered voters. That is going to be our N sample size. It shows that 412 are dissatisfied with Democratic and Republican parties. So this is going to be a proportion, 412 out of 550. So this is our X value. That's successes. So success, quote unquote, is that they're dissatisfied with both parties. Find a 90% confidence interval for the proportion of registered voters dissatisfied with both parties. So first, what's the z-value? What's the point estimate? And then what's the interval? Okay, well, let's go to the formula sheet here real quick. So we've got confidence interval for sigma unknown, and then we got confidence interval for proportion. So here we're dealing with proportions. So we want this one. So let's grab that and bring it over. And I'll do this one with both the formula and the calculator. Okay, so the z value here for part A, that's z alpha over 2. So our alpha here, this is 90% confidence interval, so that means alpha is 1 minus 0.90, which is 0.1. So then alpha over 2 is going to be 0.1 divided by 2, 0.05. So then we need z alpha over 2. So z alpha over 2 then is going to be z 0.05. So that's the z-score with 5% of the area to the right. Remember that subscript, that's the right area. So that picture looks like this. Our z 0.05 is over here. The 0.05 there is the right area. And then 100 minus 5 is 95, so 0.95 is the left area. So we want to do inverse norm to get a z-value here. And we're going to do the left area, 0.95. And then we're doing z-scores, so mean is 0, standard deviation 1. So let's go ahead and do that. So let me clear this out of here. So second variables, we're doing inverse norm number 3. We had 0.95 area set from our last one. We just need to change mean to 0, standard deviation to 1. Come down and make sure it's left area is 0.95. Paste it, and that's 1.645. Part B, we need our point estimate here, which is the sample proportion. So the sample proportion, that's the P prime here. And P prime is X divided by N. So successes out of total. So for us, that's 412 out of 550. Whoops, sorry about that. Let's compute that. 0.74909, so 0.749. Okay, and now we're going to go ahead and form our confidence interval here. So let's first do our margin of error right here. So our z alpha over 2 is going to be z.05. And then we're multiplying by square root of p prime 749. Oh, let's go ahead and do the formula here. So this is going to be p prime 1 minus p prime over n. So our z value out in front, 1.645, square root 0.749, 1 minus 0.749, and then we're dividing by n as 550. Let's compute this on the calculator. So 1.645 times, and we need a square root in there. I'm going to do a horizontal fraction, alpha y equal enter. On the top, we've got 0.749, parentheses 1 minus 0.749. Close it up, down to the bottom, 550. 645. Yep, looks good. So 0.304, so 0.03. So this is approximately 0.030 to 3 decimal places. And that was our margin of error. We called that E, margin of error. So then our lower bound here is going to be our sample proportion, which is the 0.749, and then subtract our margin of error, 0.030. And then our upper bound will be the 0.749, and we will add the 0.030. So let's see, this will be 0.746, and then 49 and 3, 0.752. So our 90% confidence interval is 746 to 0.752. So we are 90% confident that the true population proportion is between 74.6% and 75.2%. Oh, wait a minute. I did 003. The 3 should come off in here. So 74 minus 3 is 71. That should actually be 719. And then 74 plus 3 is 77, so 779. So 719 to 749. That's what you get for doing math in your head, huh? There we go. So we're 90% confident that the true population proportion is between those. Let's do this on the calculator. So we are going to go to stat and then to tests. And we want to do a proportion interval here. So we want to scroll down. We've got one proportion z interval right there, A. So our successes, that was the 412. Our sample size, 550. And our confidence level, 0.90. And calculate. 71868, that's 719. And 7795, it'd be 780. So 719, 780, within 0.01. So this is agreeing. And then our sample proportion, it gave us 749. So a little bit of round off error because we rounded. When we got our 749, it was really 74909. So these answers are a little bit more exact, but We double check, we got the right answer. All right, and then last question. We've got a random sample of 25 Illinois drivers. So that's our sample size N. Found that they drive an average, so that's a mean, of 6 miles per hour over the speed limit. So that is going to be an X bar, a sample mean, with a sample standard deviation of 0.8. So that's telling us S is equal to 0.8. We want a point estimate, 95% confidence interval, and then we want to answer a question here. So our point estimate, part A here, our mean can be estimated by X bar, our sample mean. So our population mean estimated by our sample mean, which is 6. So no calculation there. The sample statistic is an estimate of the population parameter. 95% confidence interval, and this is for the mean. So let's go to our formulas. So confidence interval for sigma unknown. So that means we use S. So that's what we want, confidence interval for the mean. So let me grab that and bring it over. So we're going to use t-distribution here because we only know the sample standard deviation. So we need a t-value here. We've got S and we've got N. So our alpha, 95%, so that means our alpha is 0.05. So working on part B here. So alpha is 0.05. That means that alpha over 2 is going to be 0.05 divided by 2, 0.025. And then that means our t-value, t.025, is going to be inverse t is the calculator function we use for that. And then we use the left area. So I'll use the left area. So if we've got 0.025 is the area to the right of that t-value. So that's 0.025 over here. And we'll also have a 0.025 over here. And then the 95 is in the middle. So this t-value here has got 95 plus 0.025, 0.975 is the left area. And then you put in the degrees of freedom, which are 1 less than the sample size, 25 minus 1, 24. So we want this t-value here, t equals. So let's go ahead and compute that. So second variables, we want inverse t, number 4. Our left area, 0.975. Our degrees of freedom, 24. 2.0638, so 2.064. And then our margin of error, E, is going to be this part here, T alpha over 2, S over root N. So T.025, S over root N. So that's going to be 2.064. Is this T value, found it here, times our S was 0.8. Divide by square root of the sample size, which is 25. So let's go ahead and compute that. So 2.064 times 0.8 divided by, square root of 25 is 5. So 0.8 divided by 5. 0.33024, so 330 approximately. And then our lower bound is going to be the sample mean, which is the 6, minus the margin of error, 0.330. And then our upper bound is going to be the mean, sample mean 6, plus our margin of error, 0.330. So 6 minus 0.33, 5.67. And then 6 plus 0.33 would be 6.33. So that means that our confidence interval here is 5.67 to 6.33. And we are 95% confident that the population mean is in that interval. And then part C, a large study in 2015 found that the mean miles per hour over the speed limit was 5. Do we have reason to believe that the population mean miles per hour over the limit has increased, or is it more likely our results are due to chance? So if we look at our 95% confidence interval, the amount over the limit, 95 for 95% of samples, the mean is going to be, the true population mean is going to be in that interval. So this interval here goes from, so here's 5 miles per hour, here's 6 miles per hour over. So 5.67 would be about right here, up to 6.33 right there. And then they're saying in 2015, so this was an earlier study. So we just did this recent study here. So in 2015, they found the mean miles per hour over was 5 right here. And they're asking, has it increased? Well, 95% of the time, for 95% of the samples of size 25, the true population mean should be in here. 0.5 is not in there. Okay. In fact, the whole interval is higher than 0.5. So that's pretty good confirmation that, yeah, our mean has increased to something over 5. In fact, the point estimate is 6. So has it increased? Yes, since the 95% confidence interval, CI, is above, the whole interval is above 5. So that's pretty good indication that it's increased. Let's go ahead and compute this using the calculator, confirm our results from part B. So this is going to be a t interval. So we're going to go to stat and then tests. And we want a t interval right there, number 8. We are going to use summary stats. So enter, that's highlighted. Our x bar was 6. Our standard deviation sample was, what was that? 0.8. Our total sample size 25, and our confidence level 0.95. So we've got 5.669, so 5.67 to 6.33, and that's what we got here. So that is indeed confirming the work that we did by hand. So if it's a Canvas problem, you can just use calculator. If it's a written problem at the end of the test, you'll have to show the formulas. All right, very good.